Black holes have captivated humanity since Einstein's equations first hinted at their existence, becoming icons of the ultimate unknown, featured in countless films, books, and artistic expressions as portals to other dimensions, time machines, and the universe's most mysterious phenomena, representing both our greatest fears of the cosmic void and our deepest fascination with the extreme limits of physics, where the familiar rules of reality break down completely. Tonight, we're settling in for a gentle journey through one of the universe's most spectacular events, the merger of black holes. Picture yourself floating in the vastness of space, far from any earthly concerns, as we explore these cosmic dances that shake the very fabric of reality itself. The story we're about to share unfolds across billions of years, in regions where gravity becomes so intense that space and time lose their ordinary meaning, where two of the universe's most enigmatic objects spiral toward each other in an inevitable embrace that will send ripples across the cosmos. In the quiet darkness of space, far from the gentle glow of stars, events of unimaginable power unfold in perfect silence. Two black holes, each one a region where gravity has won its ultimate victory over matter, slowly circle each other in a dance that began perhaps billions of years ago. Their story is one of patience, of forces so fundamental that they shape the architecture of galaxies, yet so subtle that humanity only recently learned how to detect their whispers across the cosmic void. As we begin this journey together, let your mind drift away from the small concerns of daily life. Tonight, we're exploring phenomena that occur on scales both impossibly vast and surprisingly intimate, where objects dozens of times more massive than our sun can fit within a space smaller than a city, where time itself stretches and compresses like taffy, and where the collision of 2 points of infinite density can shake the entire universe with waves that travel at the speed of light, yet disturb matter less than the width of a proton. The discovery and understanding of black hole mergers represents one of humanity's greatest intellectual achievements. For decades, these events existed only in the abstract mathematics of Einstein's general relativity, equations on a chalkboard that suggested something so extreme that even Einstein himself doubted their physical reality. Yet here we are, in an age where we can detect the faint tremors of spacetime from collisions that occurred when the Earth was young, transforming those mathematical abstractions into real, measured phenomena that confirm our deepest theories about how the universe works. What makes black hole mergers particularly fascinating is how they combine the extremely violent with the perfectly elegant. These are events where the equivalent energy of several suns can be converted into pure gravitational radiation in a fraction of a second. Yet they follow mathematical patterns of such beauty and precision that physicists can predict their signals down to extraordinary detail. They represent nature at both its most destructive and its most creative, ending the existence of two black holes while birthing a new one, larger and more massive than either of its parents. As we explore these cosmic mergers tonight, we'll journey from the birth of black holes in the hearts of dying stars to the moment when two of these gravitational giants finally unite. We'll discover how scientists first imagined these events might occur, how they built instruments sensitive enough to detect vibrations smaller than an atomic nucleus, and what these discoveries tell us about the universe we inhabit. We'll explore the different types of black hole mergers, from stellar mass black holes that form from collapsed stars to the supermassive giants at the centers of galaxies that can be billions of times more massive than our sun. The story of black hole mergers is also a deeply human story, one of curiosity, ingenuity, and persistence. It took decades of theoretical work to understand what signals these mergers might produce. decades more to develop the technology to detect them, and the collaboration of thousands of scientists around the world to finally capture that first gravitational wave signal in September of 2015. That detection, designated GW13914, lasted just 0.2 of a second in our detectors, but it confirmed a century-old prediction and opened an entirely new way of observing the universe. Tonight, as you drift towards sleep, we'll explore this remarkable phenomenon in all its complexity and wonder. We'll begin with understanding what black holes actually are, not the science fiction versions that serve as cosmic vacuum cleaners or portals to other dimensions, but the real objects predicted by Einstein's equations and confirmed by decades of astronomical observations. We'll explore how these regions of curved spacetime form, how they grow, and most importantly, how they find each other across the vast emptiness of space. The journey of two black holes toward merger is one of the longest processes in the universe. It begins when two massive stars, perhaps born together in the same stellar nursery or brought together by the gravitational dynamics of their galaxy, each end their lives in spectacular supernova explosions, leaving behind black holes. These black holes, bound together by their mutual gravity, begin a spiral dance that can last billions of years. As they orbit each other, they slowly lose energy to gravitational waves, ripples in space-time itself that carry away their orbital energy with perfect efficiency, drawing them ever closer together. This process accelerates dramatically as the black holes approach each other. What begins as a stately waltz lasting eons becomes a frantic whirl in the final moments, with the black holes racing around each other hundreds of times per second before finally merging in an event that briefly outshines all the stars in the observable universe, not in light, which cannot escape a black hole, but in gravitational waves that ripple outward at the speed of light, carrying the news of this cosmic union to the farthest corners of the universe. To understand black hole mergers, we must first understand black holes themselves, and that story begins with stars, those brilliant furnaces that light up the night sky and make life as we know it possible. Every black hole that participates in these cosmic mergers was once a star, burning bright with nuclear fusion, holding itself up against its own gravity through the outward pressure of radiation. But stars, even the most massive ones, cannot burn forever, and when they exhaust their nuclear fuel, gravity finally wins its patient battle. The process of black hole formation is one of the most extreme events in nature, yet it follows from simple, elegant physics. Stars maintain their stability through a delicate balance between two competing forces. On one side, there's gravity, always pulling inward, trying to compress the star into the smallest possible space. On the other side, there's the outward pressure from nuclear fusion in the star's core, where hydrogen atoms slam together with such force that they fuse into helium, releasing tremendous amounts of energy in the process. This energy, in the form of radiation and heat, pushes outward, holding the star up against its own weight. For most of a star's life, this balance holds steady. Our own sun has maintained this equilibrium for about 4.5 billion years, and will continue to do so for roughly another 5 billion years. But the more massive a star is, the faster it burns through its nuclear fuel. While our sun will live for about 10 billion years total, a star 20 times more massive might live only a few million years, a cosmic eye blink. These massive stars burn so hot and bright that they can be seen across vast distances, but their brilliance comes at a price. As a massive star ages, it develops a complex internal structure, like an onion with multiple layers. The core, where temperatures and pressures are highest, fuses heavier and heavier elements as the lighter ones are exhausted. First, hydrogen fuses into helium, then helium into carbon and oxygen, then those into neon, magnesium, silicon, and finally iron. Each stage of fusion releases less energy than the one before, and each stage proceeds more quickly. While a massive star might fuse hydrogen for millions of years, the final stage of silicon fusion might last only a day. Iron represents a critical turning point in stellar evolution. Unlike all the lighter elements, iron cannot release energy through fusion. In fact, fusing iron into heavier elements requires energy input rather than releasing it. When a massive star's core becomes dominated by iron, it has reached the end of the line. No more energy can be extracted through fusion, and suddenly, catastrophically, the outward pressure that has held the star up for millions of years vanishes. What happens next occurs with breathtaking speed. Without the support of radiation pressure, the iron core collapses under its own gravity. In less than a second, actually, in about the time it takes to blink your eyes, the core of a star that might have been larger than Earth shrinks down to a sphere just a few dozen kilometers across. The density becomes so extreme that protons and electrons are crushed together to form neutrons, releasing a flood of neutrinos that carry away vast amounts of energy. The outer layers of the star, suddenly finding themselves without support, come crashing down onto this incredibly dense core. When they hit, they bounce back with tremendous force, creating a shockwave that races outward through the star. This is a supernova explosion, one of the most energetic events in the universe. For weeks or months, a single exploding star can outshine an entire galaxy containing billions of stars. The explosion is so powerful that it forges elements heavier than iron, gold, uranium, platinum, and blasts them into space, seeding future generations of stars and planets with the heavy elements necessary for chemistry and life. But what remains at the centre after this cosmic fireworks display depends on the mass of the original star. If the star was between about 8 and 20 times the mass of our Sun, the collapsed core becomes a neutron star, an object so dense that a teaspoon of its material would weigh as much as a mountain. But if the original star was more massive, even the pressure of neutrons touching each other cannot hold up against gravity. The core continues to collapse, and nothing in the known universe can stop it. This runaway collapse creates a black hole, a region of space where gravity has become so strong that nothing, not even light, can escape once it passes a certain boundary called the event horizon. The matter that formed the original stellar core is crushed down to a point of infinite density called a singularity, though our current physics breaks down when trying to describe what actually happens at such extreme conditions. What we can describe with confidence is the warped spacetime around this singularity, where the familiar rules of space and time are twisted beyond recognition. The size of a black hole's event horizon depends on its mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers, the entire mass of our star compressed into a region smaller than a city. For a black hole 10 times more massive, the event horizon would be 30 kilometers in radius. This relationship is perfectly linear, double the mass, double the radius of the event horizon. It's one of the surprisingly simple relationships in black hole physics, standing in stark contrast to the complex non-linear processes that create these objects. But not all black holes are created equal, and understanding their diversity is crucial to understanding their mergers. The black holes formed from collapsed stars, called stellar mass black holes, typically range from about 3 to several dozen times the mass of our Sun. Below 3 solar masses, the collapsed core can stabilize as a neutron star rather than continuing to collapse into a black hole. Above about 50 or 60 solar masses, it becomes difficult for stars to form in the first place, as they would generate so much radiation that they would blow themselves apart. However, the universe has ways of creating black holes much more massive than what single stars can produce. In the early universe, when the first stars formed from pristine hydrogen and helium without any heavier elements to help cool the gas, stars could grow to hundreds of times the mass of our Sun. These population 3 stars, as astronomers call them, would have lived fast and died young, creating the first black holes when the universe was only a few 100 million years old. These primordial black holes could have been the seeds that grew into the supermassive black holes we see at the centres of galaxies today. There's another pathway to black hole formation that bypasses stellar evolution entirely. In the extremely early universe, just fractions of a second after the Big Bang, regions of space that happened to be slightly denser than average could have collapsed directly into black holes. These primordial black holes could have a wide range of masses, from microscopic ones that would have evaporated through Hawking radiation long ago to massive ones that could still exist today. While we haven't definitively detected primordial black holes, they remain an active area of research and could potentially explain some of the dark matter in the universe. The formation of a black hole fundamentally changes the nature of space and time in its vicinity. Near a black hole, time flows differently than it does in flat space. An observer falling toward a black hole would experience time normally from their perspective, but to an outside observer, they would appear to slow down as they approach the event's horizon. Their final moments before crossing stretched out to infinity. This time dilation is not science fiction. It's a real effect predicted by Einstein's general relativity and confirmed by observations of objects orbiting close to black holes. The space around a black hole is also dramatically warped. Light rays that would travel in straight lines through empty space follow curved paths near a black hole. This gravitational lensing can create multiple images of objects behind the black hole, or even Einstein rings, perfect circles of light from a distant source that happens to be directly behind the black hole from our perspective. The warping of space is so extreme that close to a rotating black hole, space itself is dragged around in the direction of rotation, an effect called frame dragging that would force any object to rotate along with the black hole. Understanding how individual black holes form and behave is essential to understanding what happens when 2 of them encounter each other. Each black hole brings to the merger its own mass, its own spin, and its own history. Some might be the remnants of the universe's first stars, ancient objects billions of years old. Others might be relatively young, formed from stars that died when the universe was already full of galaxies and heavy elements. Some might be spinning rapidly, having absorbed material from a companion star, or simply retained the angular momentum of their progenitor star. Others might be barely spinning at all. The diversity of black holes means that their mergers can proceed in various ways. 2 non-spinning black holes will merge differently than 2 rapidly spinning ones. Black holes spinning in the same direction will merge differently than those spinning in opposite directions. Black holes of similar mass will merge differently than cases where one black hole is much more massive than the other. Each configuration produces its own unique pattern of gravitational waves, its own signature in the fabric of spacetime that carries information about the properties of the merging black holes across the universe. As we contemplate these cosmic giants and their violent births, it's worth taking a moment to appreciate the profound mystery they represent. Black holes are regions where our normal understanding of physics breaks down, where the finite meets the infinite, where time can stop and space can be twisted into configurations that defy ordinary imagination. Yet despite their extreme nature, or perhaps because of it, black holes follow beautifully simple mathematical laws. They are completely characterized by just 3 properties: mass, electric charge, and angular momentum or spin. This is sometimes called the no-hair theorem, expressing the idea that black holes have no other distinguishing features, no hair that would make one black hole different from another with the same mass, charge, and spin. To truly appreciate the magnificent phenomenon of black hole mergers, we need to step back and understand the stage on which these cosmic dramas play out, space-time itself. The merger of two black holes is not simply two objects coming together like balls colliding on a pool table. It's a dynamic reshaping of the very fabric of reality, where space and time themselves become fluid, bending and rippling in response to the enormous gravitational fields involved. Before Einstein revolutionized our understanding of gravity, we lived in Newton's universe, a cosmos where space was like an infinite, unchanging stage on which objects moved, and time ticked along at the same rate everywhere, providing a universal clock by which all events could be measured. Gravity, in Newton's view, was a force that reached instantly across space, pulling objects toward each other with a strength that depended on their masses and the distance between them. This view worked remarkably well for most purposes, and still does for calculating planetary orbits or launching satellites. But Newton's gravity had some troubling features. How could one mass instantly know about the existence of another mass across vast distances of empty space? What was the mechanism by which this force operated? Newton himself was uncomfortable with these questions, famously writing that he would frame no hypotheses about the underlying nature of gravitational attraction. For over 2 centuries, these questions lingered at the edges of physics, troubling but not urgent, as Newtonian gravity worked so well for practical purposes. Einstein changed everything with his general theory of relativity, published in 1915. In Einstein's vision, gravity is not a force at all, but rather the curvature of spacetime itself. Mass and energy bend the fabric of spacetime, and objects moving through this curved spacetime follow the straightest possible paths, which we perceive as gravitational attraction. The Earth orbits the Sun not because of some invisible force pulling it, but because the Sun's mass curves the spacetime around it, and Earth is simply following the straightest path through that curved geometry. This might sound abstract, but we can visualize it with analogies, though we must remember that all analogies are imperfect when dealing with 4-dimensional spacetime. Imagine a stretched rubber sheet. Place a bowling ball in the center, and it creates a depression. Now roll a marble near the bowling ball. The marble will curve around the depression, and if you give it just the right speed, it will orbit around the bowling ball. The marble isn't being pulled by a force. It's simply following the curved surface of the sheet. But spacetime curvature is far more subtle and complex than this simple analogy suggests. It's not just space that curves, but time as well. Near a massive object, time actually flows more slowly relative to regions farther away. This isn't science fiction. It's a measurable effect that must be accounted for in GPS satellites, which experience time flowing slightly faster in their orbits than we do on Earth's surface. Without corrections for this relativistic time dilation, GPS systems would accumulate errors of several kilometers per day. The mathematics that describes curved spacetime is beautiful but complex, involving tensors, mathematical objects that can encode how distances and angles change from point to point in curved space. The Einstein field equations, which relate the curvature of spacetime to the energy and momentum within it, are a set of 10 coupled, non-linear partial differential equations. Solving them exactly is possible only in highly symmetric situations. For something as complex as 2 black holes spiraling together, we need powerful computers running for weeks or months to find solutions. What makes black holes special in this geometric view of gravity is that they represent regions where spacetime curvature becomes extreme, technically infinite at the singularity. The event horizon of a black hole is not a physical surface, but rather a boundary in space-time, the point of no return beyond which the curvature is so extreme that all paths, all possible futures, lead inexorably toward the singularity. It's not that you need infinite speed to escape from inside the event horizon, it's that there literally is no path through space-time that leads outward once you've crossed this boundary. When two black holes orbit each other, they create a constantly changing pattern of space-time curvature. Each black hole warps the space around it, and these warped regions interact in complex ways. As the black holes move, the curvature patterns shift and flow, like two whirlpools in water circling each other, each affecting the flow patterns of the other. But unlike water, space-time has no underlying medium. It is the medium, the very fabric of reality itself that's being twisted and deformed. This dynamic space-time curvature has a remarkable consequence: gravitational waves. Just as accelerating electric charges produce electromagnetic waves, accelerating masses produce gravitational waves. But there's a crucial difference. Electromagnetic waves are disturbances that travel through space-time. Gravitational waves are disturbances of space-time itself, ripples in the fabric of reality that travel outward at the speed of light. When a gravitational wave passes through a region of space, it literally stretches and compresses distances. If a gravitational wave passed through your room right now, travelling perpendicular to the floor, it would alternately stretch the room in one direction while compressing it in the perpendicular direction, then reverse, creating an oscillating pattern of distortion. The effect is incredibly tiny. Even the strongest gravitational waves from black hole mergers change distances by less than the width of an atomic nucleus. But it's a real, physical distortion of space itself. The production of gravitational waves is intimately connected to the geometry of the source. A perfectly spherical explosion, even one as powerful as a supernova, produces no gravitational waves because the space-time curvature remains spherically symmetric. You need asymmetric acceleration of mass to generate these ripples. Two black holes orbiting each other provide the perfect gravitational wave generator, massive objects in rapid asymmetric motion. As gravitational waves carry energy away from the orbiting black holes, the system loses energy, causing the orbit to decay. This is a perfectly efficient process. Every bit of energy lost from the orbit appears in the gravitational waves. There's no friction, no heat, no light, just a pure conversion of orbital energy into ripples in space-time. This process, called gravitational radiation, was first observed indirectly in a binary pulsar system discovered by Hulse and Taylor in 1974, where the orbital decay matched Einstein's predictions so precisely that it earned them the Nobel Prize in physics. The strength of gravitational waves depends on several factors: the masses of the objects involved, how fast they're accelerating, and how far away they are from us. The waves from two orbiting black holes follow a characteristic pattern called a chirp. Early in the spiral, when the black holes are still far apart and orbiting slowly, the waves are weak and low in frequency. As the black holes spiral closer together, they orbit faster, and the waves become stronger and higher in frequency. This creates a rising tone, like a bird's chirp, that encodes information about the masses and spins of the black holes. Understanding space-time and gravity in Einstein's framework also reveals why black hole mergers are so special. These events probe the most extreme regime of gravity, where the field equations become highly nonlinear and where our usual approximations break down. Near merging black holes, space-time curvature becomes so strong that the waves themselves affect the background space-time, which in turn affects the waves, a complex feedback loop that can only be solved with sophisticated numerical techniques. The warping of space-time near black holes also leads to fascinating phenomena that affect how we observe these objects. Light from material falling into a black hole becomes gravitationally redshifted, its wavelength stretched as it climbs out of the gravitational well. For light emitted just outside the event horizon, this redshift becomes infinite. The light loses all its energy trying to escape and never reaches distant observers. This is why the event horizon appears perfectly black, giving these objects their name. Rotating black holes, which are probably the norm rather than the exception in nature, add another layer of complexity to space-time geometry. A spinning black hole drags space-time around with it, a phenomenon called the lens-theoring effect, or frame dragging. Near a rapidly rotating black hole, it becomes impossible to remain stationary relative to the distant stars. Space itself is being pulled around, and you must rotate with it. This effect extends beyond the event horizon into a region called the ergosphere, where the dragging of space-time is so strong that nothing can resist being pulled around the black hole. When two rotating black holes approach each other, their individual frame-dragging effects interact in complex ways. If they're spinning in the same direction as their orbit, the merger proceeds differently than if they're spinning in opposite directions or at angles to the orbital plane. These spin configurations affect not only the gravitational waves produced, but also the properties of the final black hole formed from the merger. The interaction of angular momentum in curved spacetime is so complex that predicting the final spin of the merged black hole requires detailed numerical simulations. The dance of spacetime curvature during a black hole merger is perhaps nature's most elegant choreography. Two regions of infinite curvature spiral around each other, their event horizons eventually touching and merging into a single, larger horizon. The merger happens from the outside in. The common event horizon forms before the singularities actually meet. For a brief moment, the merged black hole is highly distorted, not spherical, but stretched and twisted by the violence of the merger. It then rings down, oscillating like a struck bell, emitting gravitational waves at characteristic frequencies determined by its mass and spin, until it settles into a perfectly smooth stationary state. This final state illustrates one of the most remarkable features of general relativity: the uniqueness and simplicity of black holes. No matter how complex and violent the merger, no matter what the detailed properties of the original black holes, the final state is always a Kerr black hole, completely characterized by just its mass and angular momentum. All the complexity, all the information about how the black hole formed is either radiated away in gravitational waves or hidden forever behind the event horizon. The story of how two black holes find each other across the vast emptiness of space and begin their fateful dance toward merger is one of cosmic patience and astronomical odds. Space is incomprehensibly vast and mostly empty. The average density of matter in the universe is about 6 hydrogen atoms per cubic meter, a vacuum far better than anything we can create in laboratories on Earth. In this emptiness, the probability of two black holes randomly encountering each other is essentially zero. Yet black hole mergers happen regularly throughout the universe, detected now by our gravitational wave observatories at a rate of about 1 per week. How do these cosmic partnerships form? There are several pathways by which two black holes can become gravitationally bound to each other, each leaving its own subtle signatures in the eventual merger. The most straightforward scenario begins with two massive stars that are born together as a binary system. Stars rarely form in isolation. Most are born in pairs or small groups, orbiting their common center of mass from the very beginning. When both stars in such a system are massive enough to eventually form black holes, And if their orbit survives the violent supernova explosions that create those black holes, the result is a binary black hole system destined for eventual merger. This pathway from binary star to binary black hole is fraught with challenges. When the first star explodes as a supernova, the explosion is rarely perfectly symmetric. The newly formed black hole receives a kick, a sudden velocity change that can range from a few kilometers per second to over 1,000 kilometers per second. If this kick is too strong or in the wrong direction, it can unbind the binary system, sending both objects flying apart into space, never to meet again. The system must survive not one but two such explosions, each potentially catastrophic to the orbital partnership. Even if both stars successfully collapse into black holes while remaining bound to each other, they're typically left in a very wide orbit, separated by astronomical distances. Two black holes orbiting each other at a distance similar to Earth's orbit around the Sun would take hundreds of years to complete a single orbit and billions of years to merge through gravitational wave emission alone. For these widely separated binaries to merge within the age of the universe, they need help getting closer together. This help can come from a third star in the system. Many massive stars are born not in pairs but in triples or higher order multiples. Through a process called Kozai-Lidov oscillations, the gravitational influence of a third, distant star can cause the inner binary's orbit to become highly eccentric, stretched into a long ellipse, rather than a circle. During the close approaches in this eccentric orbit, gravitational wave emission is much stronger, allowing the black holes to shed orbital energy more efficiently and spiral together more quickly. Another pathway to binary black hole formation occurs in dense stellar environments like globular clusters or the nuclear star clusters at the centers of galaxies. In these crowded neighborhoods, where stars are packed thousands or millions of times more densely than in our solar neighborhood, black holes can form binary systems through dynamic interactions. Two black holes that happen to pass near each other can become bound if they lose energy through gravitational interaction with a third black hole or star. This process, called three-body capture, can create binary systems from black holes that were born completely separately, perhaps millions of years apart. These dynamically formed binaries have different characteristics than those formed from binary stars. They're more likely to have black holes of very different masses, as there's no reason for dynamically captured black holes to be similar. They're also more likely to have misaligned spins, with the black holes rotating in directions unrelated to their orbit, creating complex gravitational wave signatures during merger. The black holes in these systems might have had rich histories before finding each other. Perhaps one consumed a companion star, spinning up to near its maximum rotation rate, while the other remained isolated, a dark sentinel drifting through space. In the cores of galaxies where stellar densities are highest and massive black holes are most common, another mechanism can drive black holes together. As black holes move through the dense stellar environment, they experience dynamical friction. Not true friction, but a gravitational effect where the black hole's gravity creates a wake of slightly increased stellar density behind it, which then pulls back on the black hole, causing it to lose energy and sink toward the center of the cluster. Through this process, the most massive objects naturally segregate to the center, where they're more likely to encounter each other and form binaries. Once two black holes become gravitationally bound, their journey toward merger enters a new phase. The early stages of this journey can be incredibly slow. Two stellar mass black holes orbiting each other at a distance of 1 astronomical unit, the distance from Earth to the Sun, would take over 1 million years just to complete one orbit. At this separation, the gravitational waves they emit are incredibly weak, carrying away such a tiny amount of energy that the orbit would take longer than the current age of the universe to decay significantly. But the process is inexorable. Every orbit, no matter how slowly, radiates away some energy in the form of gravitational waves. As energy is lost, the black holes move closer together, which makes them orbit faster, which causes them to emit stronger gravitational waves, which makes them lose energy faster. A runaway process that accelerates exponentially as the black holes approach each other. What begins as an almost imperceptible spiral lasting billions of years becomes a frantic death spiral in the final seconds. The orbital evolution of a binary black hole system can be divided into 3 distinct phases, each governed by different physics and requiring different mathematical techniques to understand. In the early spiral phase, when the black holes are well separated, the system can be treated using post-Newtonian approximations, corrections to Newton's gravity that account for relativistic effects. The black holes orbit each other much like planets orbit the Sun, just with additional subtle effects from general relativity. During this slow spiral phase, the binary system acts like a cosmic lighthouse, sweeping beams of gravitational waves around as it rotates. The frequency of these waves is twice the orbital frequency. The pattern repeats twice per orbit because gravitational waves are quadrupolar, responding to the changing quadrupole moment of the mass distribution. For widely separated black holes, these waves have frequencies far below what our current detectors can sense, perhaps 1 cycle per hour or even 1 per year. As the black holes spiral closer together, tidal effects become important. While black holes themselves have no solid surface to be tidally distorted, the spacetime around them responds to their mutual gravity. Each black hole raises tides in the gravitational field of the other, creating complex patterns of spacetime curvature that affect the orbital evolution. These tidal interactions can transfer angular momentum between the black hole's spins and their orbit, causing the spins to precess, wobble like spinning tops, and potentially aligning or anti-aligning them with the orbital angular momentum. The environment around the binary black hole system can also influence its evolution. If the black holes are surrounded by gas, perhaps from a disrupted star or an accretion disk, this material can extract angular momentum from the orbit, causing the black holes to spiral together more quickly. The gas heats up as it's compressed and stirred by the orbiting black holes, potentially producing electromagnetic radiation that could serve as an early warning sign of an impending merger. However, most black hole mergers detected so far appear to occur in relatively clean environments, without significant surrounding matter. For supermassive black hole binaries formed when galaxies merge, the journey toward merger faces an additional challenge known as the final parsec problem. As these enormous black holes, millions or billions of times the mass of our Sun, orbit each other, they clear out stars from their orbital path through gravitational slingshot interactions. Once they've cleared a gap, they can no longer lose energy through these interactions and their orbital decay stalls. Getting past this final parsec, about 3 light years, requires either gravitational wave emission, which is weak at these large separations, or continued interaction with gas or stars that venture into the danger zone. The solution to the final parsec problem might involve the complex dynamics of galactic nuclei. In a galaxy merger, the central regions become violently disturbed, with stars on chaotic orbits that can continue to interact with the binary black holes. Gas flowing into the galactic center during the merger can also help, forming a circumbinary disk that torques the black holes and drives them together. Some theories suggest that many galaxies might harbor binary supermassive black holes that are stalled at this final parsec separation, waiting for some process to drive them close enough for gravitational waves to take over. As we observe more black hole mergers through gravitational waves, we're beginning to see the diversity of binary evolution pathways reflected in the data. Some mergers involve black holes of nearly equal mass, suggesting they formed from binary stars of similar mass. Others show mass ratios of 3:1, 4:1, or even higher, pointing to different formation mechanisms. The spins of the black holes, inferred from the gravitational wave signals, tell us about their history, whether they've been spun up by accreting matter or whether they've retained the angular momentum from their birth. One particularly intriguing discovery has been black holes in the so-called mass gap between about 50 and 100 solar masses. Traditional stellar evolution theory suggests that stars massive enough to create black holes in this range should be disrupted by pair instability supernova, leaving no remnant. Yet LIGO and Virgo have detected black holes in this mass range. These might be second-generation black holes, formed from the merger of smaller black holes, or they might challenge our understanding of stellar evolution and suggest that some stars can indeed create black holes in this mass range. One particularly intriguing discovery has been black holes in the so-called mass gap between about 50 and 100 solar masses. Traditional stellar evolution theory suggests that stars massive enough to create black holes in this range should be disrupted by pair instability supernova, leaving no remnant. Yet LIGO and Virgo have detected black holes in this mass range. These might be second-generation black holes, formed from the merger of smaller black holes, or they might challenge our understanding of stellar evolution and suggest that some stars can indeed create black holes in this mass range. The distribution of black hole masses and spins that we observe through gravitational waves is teaching us about the lives and deaths of massive stars throughout cosmic history. Each detection adds another piece to the puzzle, helping us understand not just individual mergers but the population of black holes throughout the universe. We're discovering that black holes are more common than we once thought, that they can be more massive than traditional theories predicted, and that they find each other and merge through a rich variety of pathways that we're only beginning to map out. The journey of two black holes toward each other is also a journey through time. The gravitational waves we detect today from a merger might have begun their journey when the universe was half its current age, travelling billions of years across expanding space to reach our detectors at just the right moment. The black holes themselves might be even older, perhaps formed from some of the first generation of stars when the universe was only a few 100 million years old. In this sense, each merger we detect is a messenger from the deep past, carrying information about conditions in the early universe that we can obtain no other way. As binary black holes spiral closer together, they enter a regime where the simple approximations of orbital mechanics break down. The space-time around them becomes so dynamically curved that we can no longer think of them as two separate objects orbiting in a fixed background. Instead, they become a single complex system of curved space-time, evolving according to the full nonlinear dynamics of Einstein's equations. This is where our story becomes truly extraordinary, where the familiar concepts of space and time lose their everyday meaning, and where nature performs calculations of such complexity that our most powerful supercomputers struggle to keep up. The gradual decay of a binary black hole orbit through the emission of gravitational waves is one of nature's most patient processes, yet it follows mathematical laws of crystalline precision. This slow spiral inward can last billions of years, each orbit imperceptibly smaller than the last, the black holes drawing together with the inevitability that nothing in the universe can prevent. Understanding this process requires us to appreciate both the weakness of gravitational waves in carrying away energy and the relentless efficiency with which they operate. When two black holes orbit each other at large separations, they're essentially following Kepler's laws, the same rules that govern planetary orbits, with small corrections from general relativity. At a separation of, say, 1,000 times the sum of their Schwarzschild radii, two equal mass black holes of 10 solar masses each would orbit each other once every few months. The gravitational waves they emit at this stage are incredibly weak, carrying away energy at a rate that would power only a few light bulbs if we could somehow harness it. Yet this tiny energy loss is enough to gradually shrink the orbit, bringing the black holes closer together over cosmic timescales. The mathematics governing this energy loss was first worked out by Einstein himself, though he doubted gravitational waves would ever be detected. The power radiated in gravitational waves depends on the fifth power of the orbital frequency and the masses of the objects involved. This strong dependence on frequency means that as the orbit shrinks and the black holes orbit faster, the energy loss accelerates dramatically. What starts as an almost negligible effect becomes the dominant force shaping the system's evolution. To put this in perspective, consider two black holes of 30 solar masses each, initially orbiting at a separation of 1 million kilometers, about twice the distance from Earth to the Moon. At this separation, they would orbit each other once every few hours and emit gravitational waves with a power of about 10 to the 37th watts. This might sound like a lot, but spread over the enormous masses involved, it would take about 1 billion years for the orbit to decay significantly. However, once the separation shrinks to 100,000 kilometers, the orbital period drops to minutes, and the power output increases by a factor of 30,000. The final inspiral from this point would take only a few years. The energy carried away by gravitational waves comes directly from the orbital energy of the system. As energy is lost, the black holes paradoxically speed up. They orbit faster, even as they lose energy. This seeming contradiction is resolved by understanding that the black holes are falling deeper into each other's gravitational potential wells. The loss of potential energy more than compensates for the gain in kinetic energy, resulting in a net energy decrease that appears as gravitational waves rippling outward through space. This process is perfectly conservative in the sense that every bit of energy lost from the orbit appears in the gravitational waves. There's no dissipation, no heat, no randomness, just a clean conversion of orbital energy into ripples in space-time. This makes gravitational wave emission fundamentally different from electromagnetic radiation or other forms of energy loss. It's a purely geometrical effect, a consequence of the way mass and energy curve space-time, and how that curvature propagates through the universe. The orbital decay process is also remarkably robust. Unlike friction or electromagnetic interactions, which depend on the detailed properties of materials or charges, gravitational wave emission depends only on the masses and velocities involved. Two black holes will spiral together in exactly the same way regardless of what they're made of, or rather, regardless of what they were made of before collapsing into black holes. This universality is a consequence of the equivalence principle, one of the foundational ideas of general relativity, which states that all forms of mass energy respond to gravity in the same way. As the black holes spiral closer together, relativistic effects become increasingly important. The concept of orbital velocity starts to lose meaning as velocities approach the speed of light. At a separation of 100 Schwarzschild radii, the black holes are moving at about 10% of light speed. At 20 Schwarzschild radii, they're approaching 30% of light speed. These velocities are so extreme that we must account for effects like relativistic mass increase, time dilation, and the fact that changes in the gravitational field propagate at finite speed rather than instantaneously. The emission of gravitational waves also carries away angular momentum from the system. This is crucial because angular momentum, like energy, is conserved, and its removal is what allows the orbit to circularize and shrink. The gravitational waves carry away angular momentum with a specific pattern. They have a helicity of 2, meaning they create a quadrupolar pattern of stretching and squeezing as they pass through space. This is different from electromagnetic waves, which have helicity 1 and create dipolar patterns. During the long inspiral phase, the orbit tends to circularize even if it starts out elliptical. Gravitational wave emission is strongest at the point of closest approach in an eccentric orbit, which preferentially removes energy from that part of the orbit, gradually making it more circular. By the time the black holes enter the final stages of inspiral that our detectors can observe, most orbits have become nearly perfect circles, though some systems retain measurable eccentricity that provides clues about their formation history. The rate of orbital decay follows a beautiful mathematical relationship known as Peters-Matthews equation, derived in 1963. For circular orbits, the rate at which the orbital radius decreases is proportional to the radius to the negative third power. This means that as the black holes get closer, the rate of inspiral increases as the cube of their separation. When they're half as far apart, they spiral together 8 times faster. When they're 1/10 as far apart, they spiral together 1,000 times faster. This runaway acceleration is what transforms the patient billion-year dance into a violent merger lasting fractions of a second. Throughout most of the inspiral, the black holes can be treated as point masses for the purpose of calculating gravitational wave emission. Their internal structure, the fact that they're black holes rather than ordinary stars, doesn't matter until they get very close together. This is another manifestation of the no-hair theorem. Black holes have no internal structure that can affect their external gravitational field beyond their mass, charge, and spin. This simplicity is what makes it possible to calculate gravitational wave signals so precisely. However, the spins of the black holes do affect the inspiral in subtle but important ways. A spinning black hole drags spacetime around with it, affecting the orbit of its companion. If the spins are aligned with the orbital angular momentum, they effectively add to it, making the system harder to unbind and slowing the inspiral slightly. If the spins are anti-aligned, they subtract from the orbital angular momentum, speeding up the inspiral. Spins perpendicular to the orbital plane cause the orbit to precess, wobbling like a spinning top, which creates characteristic modulations in the gravitational wave signal. These spin effects become more pronounced as the black holes approach each other. The spin-orbit coupling can cause the orbital plane to precess dramatically, sometimes flipping completely over the course of the inspiral. The spins themselves also precess around the total angular momentum vector, creating a complex dance of angular momenta that's encoded in the gravitational waves. By carefully analysing these signals, scientists can determine not just the masses of the merging black holes, but also their individual spins and the angle between the spins and the orbit. The energy scale of the inspiral process is staggering. Over the entire inspiral from large separation to merger, a binary black hole system can radiate away several % of its total mass energy in gravitational waves. For two 30 solar mass black holes, this amounts to converting about 3 solar masses entirely into gravitational wave energy. More energy than our Sun will produce in its entire 10 billion year lifetime, radiated away in a process lasting seconds to minutes in its observable phase. Yet despite these enormous energies, gravitational waves interact so weakly with matter that they pass through planets and stars almost completely unaffected. A gravitational wave strong enough to stretch and squeeze a kilometre-long detector by the width of a proton, would pass through Earth as if it weren't there, emerging on the other side virtually unchanged. This weakness is both a curse and a blessing. It makes gravitational waves incredibly difficult to detect, but it also means they can carry information from regions of space that are completely opaque to electromagnetic radiation. The slow spiral phase also offers our best laboratory for testing general relativity in the strong field regime. Each orbit is a test of Einstein's theory, and with modern detectors able to observe thousands of orbits in the final minutes before merger, we can check whether the observed signal matches theoretical predictions to extraordinary precision. So far, general relativity has passed every test, with observed waveforms matching predictions to within the measurement uncertainties. As we listen to the gravitational wave signals from inspiraling black holes, we're essentially hearing the universe sing. The frequency of the waves increases smoothly as the black holes spiral together, creating a characteristic chirp that rises in both pitch and amplitude. This chirp is so distinctive that it can be pulled out of detector noise using matched filtering techniques, where we compare the data to theoretical templates of what the signal should look like. Each detection is a triumph of both theoretical physics and experimental ingenuity, confirming predictions made a century ago with measurements at the edge of what's technologically possible. The transition from the slow-in spiral to the final plunge happens remarkably quickly. When the black holes reach what's called the innermost stable circular orbit, about 3 times the Schwarzschild radius for non-spinning black holes, the orderly spiral breaks down. There's no longer a stable orbit possible. The black holes plunge toward each other in a chaotic tumble that can only be calculated using numerical relativity simulations. This is where our story becomes truly extreme, where space-time itself becomes so violently distorted that our usual concepts of space and distance lose their meaning. Gravitational waves are perhaps the most elegant prediction of Einstein's general relativity, yet they remained purely theoretical for a century after their prediction. These ripples in the fabric of space-time itself carry information about the most violent events in the universe directly to us, undistorted by intervening matter, providing a completely new way to observe and understand the cosmos. When black holes merge, they create gravitational waves of such intensity that they briefly become the brightest sources in the gravitational wave sky, outshining all the stars in the observable universe combined, not in light, but in the invisible ripples of space-time itself. To truly appreciate gravitational waves, we must first understand what they are at the most fundamental level. In Einstein's theory, space and time are not rigid and unchanging, but dynamic and flexible, capable of being stretched, compressed, and twisted by the presence of mass and energy. When masses accelerate in certain ways, they create time-varying distortions in space-time that propagate outward at the speed of light. These propagating distortions are gravitational waves, literally ripples in the geometry of space and time. Imagine space-time as a vast, flexible fabric. A massive object, like a black hole, creates a depression in this fabric, curving the space around it. Now imagine 2 black holes orbiting each other. As they move, they create changing patterns of curvature that ripple outward like waves on a pond. But unlike water waves, which are disturbances in a medium, gravitational waves are disturbances of the medium itself. Space and time are what's waving. The effect of a passing gravitational wave is to alternately stretch and compress space in perpendicular directions. If a gravitational wave were passing through your room right now, travelling vertically upward through the floor, it would cause the room to become slightly longer in the north-south direction, while simultaneously becoming shorter in the east-west direction, then reverse oscillating back and forth at the frequency of the wave. The key word here is slightly. Even the strongest gravitational waves from black hole mergers change distances by less than 1 part in 10 to the 21st, smaller than an atomic nucleus compared to the distance from Earth to the Sun. This incredible weakness is why gravitational waves remained undetected for so long, despite their theoretical prediction. Einstein himself flip-flopped on whether gravitational waves were real physical phenomena or just mathematical artifacts of the coordinate systems used in general relativity. It wasn't until the 1950s and 60s that physicists reached consensus that gravitational waves were real and could, in principle, carry energy and information through space. The theoretical foundation for understanding gravitational waves comes from linearized general relativity, an approximation valid when spacetime is only slightly curved. In this approximation, the Einstein field equations, normally a forbidding set of nonlinear partial differential equations, simplify to something resembling the wave equation familiar from electromagnetism. This mathematical similarity is not coincidental. Both electromagnetic and gravitational waves arise from the requirement that changes in fields propagate at finite speed rather than instantaneously. But there are crucial differences between electromagnetic and gravitational waves that make the latter both more difficult to detect and more informative when we do detect them. Electromagnetic waves are dipolar. They arise from the acceleration of electric charges with positive and negative charges creating opposing contributions. Gravitational waves are quadrupolar. They arise from the acceleration of mass, but since there's no such thing as negative mass, the lowest order radiation comes from the quadrupole moment of the mass distribution. This means gravitational waves have a different symmetry pattern and carry different information than electromagnetic waves. The energy carried by gravitational waves is enormous in absolute terms, but tiny compared to the masses involved in creating them. When two black holes merge, they can radiate away several solar masses worth of energy in gravitational waves in less than a second, a power output briefly exceeding all the stars in the observable universe combined. Yet this represents only a few percent of the total mass of the system. The efficiency of gravitational wave generation is proportional to the square of the gravitational potential, which even near black holes is much less than 1. The propagation of gravitational waves through space is remarkably clean. Unlike electromagnetic waves, which can be absorbed, scattered, or refracted by matter, gravitational waves pass through matter almost completely unaffected. A gravitational wave from a black hole merger billions of light-years away travels through all the intervening galaxies, stars and dust clouds without being significantly altered. This means gravitational waves can bring us information from regions of space that are completely opaque to electromagnetic observations, such as the first fraction of a second after the Big Bang or the interiors of stellar explosions. The frequency of gravitational waves from black hole mergers spans a wide range, from millihertz for widely separated, supermassive black holes to kilohertz for the final moments of stellar mass black hole mergers. Our current ground-based detectors are sensitive to frequencies from about 10 Hz to a few thousand Hz, perfectly matched to the final seconds of stellar mass black hole mergers. Future space-based detectors will be sensitive to lower frequencies, allowing us to observe supermassive black hole mergers and the earlier stages of stellar mass black hole in spirals. The waveform, the pattern of stretching and squeezing over time, from a black hole merger encodes a wealth of information about the source. The frequency evolution tells us about the masses of the black holes. The amplitude tells us about the distance to the source. The phase evolution tells us about the spins of the black holes. The polarization tells us about the orientation of the orbital plane. By carefully analyzing all these aspects of the signal, we can reconstruct the properties of the merging black holes with remarkable precision. The detection of gravitational waves requires measuring distance changes smaller than an atomic nucleus over kilometer scales. This seemingly impossible task is accomplished using laser interferometry. The Laser Interferometer Gravitational Wave Observatory, or LIGO, consists of two 4-kilometer-long arms arranged in an L shape. Laser light bounces back and forth between mirrors at the ends of the arms, and the light from the two arms is combined to create an interference pattern. When a gravitational wave passes through, it changes the length of the arms differently, altering the interference pattern in a measurable way. The technical challenges involved in making these measurements are staggering. The mirrors must be isolated from all sources of vibration, seismic noise, thermal noise, even the quantum fluctuations of the laser light itself. The laser must be extraordinarily stable. The vacuum in the arms must be better than interstellar space, and the entire system must be controlled with exquisite precision. It's a testament to human ingenuity that we can make these measurements at all. The first direct detection of gravitational waves on September 14th, 2015, marked the beginning of a new era in astronomy. The signal, designated GW1P0914, came from the merger of two black holes, about 36 and 29 solar masses, located about 1.3 billion light-years away. The entire observable signal lasted about 0.2 of a second, during which the black holes completed about 8 orbits before merging. The energy radiated in gravitational waves was equivalent to 3 solar masses, more energy than all the stars in the observable universe emit as light in the same time. Since that first detection, we've observed dozens of black hole mergers, each one teaching us something new about black holes and gravity. We've seen black holes more massive than we expected, spinning faster than we thought possible, and in configurations that challenge our understanding of how they form. We've tested general relativity in regimes it's never been tested before, and so far, Einstein's theory has passed every test with flying colours. The gravitational waves from black hole mergers also serve as standard sirens, sources whose intrinsic brightness we can calculate from the observed signal. By comparing the intrinsic brightness to the observed amplitude, we can determine the distance to the source independently of electromagnetic observations. This provides a completely new way to measure cosmic distances and study the expansion of the universe. One of the most remarkable aspects of gravitational wave astronomy is how much information we can extract from signals that last only fractions of a second. The merger of two black holes compresses billions of years of orbital evolution into a brief chirp that we can analyze to determine masses to within a few percent, spins to within 10 or 20%, and distances to within perhaps 30%. Each detection is like a fossil, preserving information about the lives and deaths of massive stars that existed billions of years ago. The future of gravitational wave astronomy is incredibly bright. Advanced LIGO and Virgo are being upgraded to even greater sensitivity, and new detectors are being built in Japan and India. The space-based Laser Interferometer, Space Antenna, or LISA, will detect lower frequency gravitational waves from supermassive black hole mergers. Pulsar timing arrays are searching for even lower frequency waves from the cosmic population of supermassive black hole binaries. Each of these different observatories will reveal different aspects of the gravitational wave universe. As our gravitational wave observatories become more sensitive, we're beginning to resolve the cosmic gravitational wave background, the combined signal from all the black hole mergers throughout the universe that are too faint to detect individually. This background is like a cosmic symphony, with each merger contributing its own note to the overall sound. By studying this background, we can learn about the population of black holes throughout cosmic history, how they form, how they find each other, and how they've shaped the evolution of galaxies. Gravitational waves also offer the tantalizing possibility of observing phenomena we can't see any other way. If dark matter consists of primordial black holes, their mergers would produce a distinctive gravitational wave signature. If cosmic strings exist, hypothetical one-dimensional defects in spacetime from the early universe, they would produce gravitational waves when they oscillate or intersect. Even the Big Bang itself should have produced gravitational waves that might still be detectable today as a cosmic gravitational wave background from the first fraction of a second after the universe began. The final moments before two black holes merge represent one of the most extreme phenomena in the universe, where the orderly spiral that may have lasted billions of years transforms into a violent reorganization of space-time itself. In these last fractions of a second, the black holes race around each other at appreciable fractions of the speed of light. Space-time becomes so dynamically curved that our usual concepts of distance and time lose meaning, and the energy output in gravitational waves briefly exceeds the combined luminosity of all the stars in the observable universe. This is nature at its most extreme, yet also at its most precisely calculable, following the elegant mathematics of Einstein's general relativity down to the smallest detail. As the black holes approach what physicists call the innermost stable circular orbit, or ISCO, the character of their motion fundamentally changes. Outside the ISCO, stable circular orbits are possible. An object can orbit indefinitely at a fixed radius if undisturbed. But inside the ISCO, no circular orbits are stable. Any small perturbation causes the object to either escape to infinity or plunge toward the black hole. For non-spinning black holes, the ISCO occurs at 3 times the Schwarzschild radius. For rapidly spinning black holes, it can be much closer, down to half the Schwarzschild radius for maximum spin in the same direction as the orbit. The transition through the ISCO marks the beginning of the plunge phase. The black holes no longer spiral gradually inward, but fall toward each other in a complex non-circular trajectory. The motion becomes truly relativistic, with velocities approaching half the speed of light or more. At these speeds, effects like length contraction, time dilation, and the relativistic increase in mass become dominant. The black holes are moving so fast that light signals take appreciable time to travel between them, meaning that each black hole is responding to where its companion was, not where it is. During this plunge phase, the emission of gravitational waves reaches its peak. The luminosity in gravitational waves can exceed 10 to the 56th watts, a number so large it's difficult to comprehend. For comparison, the Sun's luminosity is about 4 times 10 to the 26 watts, so the merging black holes briefly shine with the power of 10 to the 30 suns in gravitational waves. This enormous power output lasts only milliseconds, but in that brief time, more energy is radiated than our Sun will produce in its entire lifetime. The gravitational wave frequency during the final plunge increases rapidly, sweeping upward through a range that our detectors are sensitive to. For stellar mass black holes, the frequency rises from tens of hertz to hundreds or even thousands of hertz in less than a second. This rapid frequency evolution creates the characteristic chirp signal that's become the signature of black hole mergers. The amplitude of the waves also increases dramatically, making the final moments by far the loudest part of the signal. As the black holes get closer together, their individual event horizons begin to distort. The intense gravitational field of each black hole pulls on the spacetime around its companion, stretching the event horizons toward each other. These distortions grow more pronounced until, at a critical moment, the two event horizons touch. This first contact doesn't happen at a single point but along a circle, creating a brief configuration where the event horizon has a toroidal or donut-like topology. The moment of horizon merger is particularly fascinating from a theoretical perspective. The event horizon is not a physical surface but a boundary in spacetime, the point of no return beyond which nothing can escape. When the two horizons touch, they immediately merge into a single horizon that encompasses both black holes. This happens from the outside in. The common event horizon forms before the singularities at the centers of the black holes actually meet. For a brief moment, you have a single event horizon containing two singularities, though this configuration is highly unstable and rapidly evolves toward a single, larger black hole. The mathematics describing this merger process is extraordinarily complex. The Einstein field equations, which are already non-linear partial differential equations, become so complicated in this regime that they can only be solved numerically using supercomputers. These numerical relativity simulations divide spacetime into a grid and evolve the metric, the mathematical object that describes the geometry of spacetime, forward in time using sophisticated algorithms. A single simulation of a black hole merger can require millions of CPU hours and generate terabytes of data. The development of numerical relativity was itself a decades-long struggle. Early attempts in the 1960s and 70s failed due to instabilities in the numerical schemes. It wasn't until the mid-2000s that breakthroughs in formulation and gauge choices allowed stable long-term simulations of black hole mergers. These simulations are now so accurate that they can predict the gravitational waveforms to better than 1% accuracy, precise enough to extract detailed information from observed signals. During the merger, the concept of space and time becomes fluid in a very literal sense. The spacetime around the merging black holes is so dynamically curved that there's no unique way to define spatial distances or synchronize clocks. Different coordinate systems give different descriptions of what's happening, though they all agree on the physical observables like the gravitational waves produced. This coordinate ambiguity is not a weakness of the theory, but a fundamental feature. It reflects the fact that space and time are not absolute but depend on the observer's frame of reference. The merger process is remarkably efficient at converting mass into gravitational wave energy. Typically, about 5% of the total mass of the system is radiated away. For two 30 solar mass black holes, this means about 3 solar masses are converted entirely into gravitational waves. This mass energy conversion is far more efficient than nuclear fusion, which converts only about 0.5% of mass into energy. It's the most efficient energy conversion process known in the universe, approaching the theoretical maximum allowed by general relativity. The spins of the merging black holes play a crucial role in determining the details of the merger. If both black holes are spinning in the same direction as their orbit, the merger proceeds somewhat more gently, with the black holes spiraling together from a closer separation. If they're spinning in opposite directions, the merger is more violent, with the black holes plunging together from a larger separation. Misaligned spins cause the orbital plane to precess, creating complex modulations in the gravitational wave signal that encode information about the spin orientations. One of the most interesting phenomena during merger is the kick velocity imparted to the final black hole. When the two black holes have unequal masses or misaligned spins, the gravitational waves are emitted asymmetrically, carrying away linear momentum preferentially in one direction. By conservation of momentum, the merged black hole recoils in the opposite direction. These kick velocities can be substantial, up to several thousand kilometers per second for certain spin configurations, enough to eject the black hole from its host galaxy entirely. The merger process also demonstrates the cosmic censorship hypothesis, the idea that singularities in general relativity are always hidden behind event horizons. Even during the violent reorganization of spacetime during merger, the singularities remain cloaked. No naked singularities are created, preserving the causal structure of spacetime and preventing the paradoxes that naked singularities might create. This seems to be a fundamental feature of general relativity, though a complete proof remains elusive. As we observe more black hole mergers, we're beginning to see subtle variations in the merger process that tell us about the properties of the black holes involved. The exact shape of the waveform during merger depends on the mass ratio, the individual spins, and the angle between the spins and the orbital angular momentum. By comparing observed signals to libraries of numerical simulations, we can extract these parameters and learn about the black hole's properties and history. The merger phase also offers our most stringent tests of general relativity. The spacetime curvature during merger is so extreme that any deviations from Einstein's theory would be amplified. So far, every observed merger has matched the predictions of general relativity to within measurement uncertainties. This includes tests of the no-hair theorem, the idea that black holes are completely characterized by their mass and spin, and searches for exotic effects like quantum corrections to gravity. The energy scales involved in black hole mergers are so extreme that they might probe physics beyond general relativity. Some theories of quantum gravity predict corrections to the gravitational wave signal that would become apparent during the merger phase. Others suggest that the event horizon might not be absolute, allowing some information to escape. While we haven't seen evidence for any of these exotic effects yet, each new detection provides another opportunity to test the limits of our understanding. The moment of merger also marks a transition in our mathematical description of the system. Before merger, we can think of two distinct black holes with their own masses and spins. After merger, we have a single black hole with new properties. The mass of the final black hole is less than the sum of the initial masses due to the energy radiated in gravitational waves. The spin of the final black hole depends on the spins of the initial black holes and their orbital angular momentum in a complex way that can only be calculated through numerical simulations. After the violent climax of merger, when two black holes have united into one, the newly formed black hole finds itself in a highly distorted, non-equilibrium state. Like a struck bell that rings with characteristic tones, this distorted black hole oscillates, radiating away its deformations as gravitational waves until it settles into a perfectly smooth, stationary configuration. This ring-down phase, though briefer and quieter than the merger itself, carries unique information about the final black hole and provides some of our most direct tests of general relativity's predictions about black hole physics. The initial state of the merged black hole is far from the serene symmetric configuration we associate with isolated black holes. The violent reorganization of spacetime during merger leaves the event horizon distorted, bulging and twisted in complex patterns. The spacetime around the black hole churns with gravitational radiation, and the entire system vibrates with characteristic frequencies determined by the mass and spin of the newly formed black hole. These vibrations, called quasi-normal modes, are the black hole's way of shedding its distortions and settling into equilibrium. The concept of quasi-normal modes is central to understanding the ring-down phase. Unlike the normal modes of a vibrating string or drumhead, which can oscillate forever in the absence of damping, the oscillations of a black hole are intrinsically damped. The black hole cannot sustain oscillations indefinitely because any distortion of the event horizon generates gravitational waves that carry energy away to infinity. This is why they're called quasi-normal modes. They're almost like normal modes but with built-in damping. Each quasi-normal mode has a characteristic frequency and damping time that depends only on the mass and spin of the black hole. This is a remarkable consequence of the no-hair theorem. The final black hole has no memory of how it was formed, no lingering features from its progenitors. Whether it formed from the merger of two black holes, the collapse of a massive star, or any other process, a black hole with a given mass and spin will ring with exactly the same frequencies. It's as if every black hole of the same mass and spin is an identical tuning fork, producing the same pure tones when struck. The dominant mode in the ring down is typically the fundamental quadrupole mode, which has the lowest damping rate and therefore lasts the longest. For a non-spinning black hole of 10 solar masses, this mode has a frequency of about 1200 Hz and a damping time of about 4 milliseconds. The frequency scales inversely with mass, so more massive black holes ring at lower frequencies, while the damping time scales linearly with mass, so more massive black holes ring for longer in absolute terms, though for fewer cycles. The ring-down waveform can be decomposed into a sum of exponentially damped sinusoids, each corresponding to a different quasi-normal mode. The relative amplitudes of these modes depend on how the black hole was formed. A head-on collision excites different modes than an inspiraling merger, and the specific configuration of the merging black holes affects which modes are strongly excited. By analysing the ring-down signal, we can not only measure the mass and spin of the final black hole, but also test whether it truly behaves as general relativity predicts. One of the most elegant aspects of the ring-down phase is how it demonstrates the efficiency of black holes at radiating away distortions. Within a few damping times, typically milliseconds for stellar mass black holes, the black hole settles into an almost perfect Kerr solution, the exact mathematical description of a rotating black hole in general relativity. Any deviation from this perfect configuration, whether it's a bulge on the event horizon or a asymmetry in the surrounding spacetime, is radiated away as gravitational waves with remarkable efficiency. The mathematics describing quasi-normal modes comes from studying perturbations of black hole spacetimes. By considering small deviations from the equilibrium configuration and linearizing Einstein's equations around this background, physicists can derive wave equations that govern the evolution of these perturbations. The quasi-normal mode frequencies emerge as the complex eigenvalues of these wave equations, with the real part giving the oscillation frequency and the imaginary part giving the damping rate. The spectrum of quasi-normal modes is incredibly rich. Beyond the fundamental mode, there are overtones with higher frequencies and faster damping rates, as well as modes with different angular patterns. Each mode is characterized by three numbers: the angular degree, the azimuthal number, and the overtone number, much like the quantum numbers that characterize electron orbitals in atoms. The full spectrum of modes forms a unique fingerprint for each black hole, completely determined by its mass and spin. Recent observations have begun to detect not just the fundamental mode, but also overtones in the ring-down signal. This is particularly exciting because it allows for more precise tests of general relativity. With just the fundamental mode, we can measure the mass and spin of the final black hole. With one overtone, we can test whether these two modes are consistent with coming from the same black hole. With multiple overtones, we can perform increasingly stringent tests of the no-hair theorem and search for deviations from general relativity. The ring-down phase also provides insights into the thermodynamics of black holes. As the black hole settles into equilibrium, its surface area increases monotonically, consistent with the second law of black hole thermodynamics. The energy radiated in gravitational waves during ring-down represents the black hole shedding its excess energy and angular momentum, much like a hot object cooling down by radiating heat, though the mechanism is purely gravitational rather than thermal. The connection between black holes and thermodynamics is one of the most profound discoveries in theoretical physics. Black holes obey laws remarkably similar to the laws of thermodynamics, with the area of the event horizon playing the role of entropy and the surface gravity playing the role of temperature. During the ring-down phase, we can actually observe these thermodynamic principles in action. The area of the event horizon never decreases, even as the black hole radiates enormous amounts of energy in gravitational waves. This is Hawking's area theorem in action, confirmed observationally for the first time through gravitational wave observations. The ring-down signal carries information not just about the final black hole, but about the entire merger process. By analysing the specific mix of quasi-normal modes excited during ring-down, scientists can infer details about how the merger proceeded, whether it was a head-on collision or a grazing encounter, whether the black holes had aligned or misaligned spins, and how much energy and angular momentum were radiated during the merger itself. Each merger has its own characteristic ring-down signature, like a fingerprint of the specific collision that created it. The damping of quasi-normal modes during ring-down is remarkably efficient. Within just a few milliseconds for stellar mass black holes, or seconds for supermassive black holes, the violent distortions from merger are completely erased. The black hole forgets its tumultuous birth and settles into a state of perfect equilibrium, described exactly by the Kerr solution to Einstein's equations. This rapid approach to equilibrium is unlike anything in ordinary physics, where relaxation processes typically involve many intermediate steps and can take arbitrarily long times. The mathematical beauty of the ring-down phase lies in its simplicity emerging from complexity. The merger itself requires sophisticated numerical simulations to understand, but the ring-down can be described analytically using perturbation theory. The quasi-normal mode frequencies can be calculated exactly for any given mass and spin, providing precise predictions that can be compared with observations. This makes the ring-down phase particularly valuable for testing general relativity and searching for new physics. Recent advances in detector sensitivity have allowed scientists to observe not just the fundamental ring-down mode, but also overtones, higher frequency modes that decay more quickly. Detecting these overtones is like hearing not just the fundamental tone of a bell, but also its harmonics. Each additional overtone provides an independent measurement of the black hole's mass and spin, allowing for consistency checks that test whether the black hole truly behaves as general relativity predicts. So far, all observations are consistent with theoretical predictions, but as detectors improve, we'll be able to perform increasingly stringent tests. The ring-down phase also connects to deep questions about the nature of spacetime and gravity. Some theories beyond general relativity predict that black holes might have additional hair, properties beyond mass, charge, and spin that would affect their quasi-normal mode spectrum. Others suggest that quantum effects might modify the ring-down signal in subtle ways. While we haven't detected any such deviations yet, each new observation provides another opportunity to search for physics beyond Einstein's theory. The duration of the ring-down phase scales with the mass of the black hole. For a 10 solar mass black hole, the ring-down lasts only a few milliseconds. For a 100 solar mass black hole, it lasts a few hundredths of a second. For supermassive black holes, millions of times the mass of the Sun, the ring-down could last minutes or hours. This scaling means that different gravitational wave detectors, sensitive to different frequency ranges, will observe ring-down signals from different populations of black holes. The energy radiated during ring-down, while substantial, is much less than during the merger itself. Typically, the ring-down carries away less than 1% of the black hole's mass in gravitational waves, compared to several percent during the inspiral and merger. Yet this energy is radiated in a very pure form, nearly sinusoidal waves at specific frequencies, making the ring-down signal particularly clean and easy to analyze despite its lower amplitude. The transition from merger to ring-down is not sharp but gradual. The highly nonlinear dynamics of merger gradually give way to the linear perturbations of ring-down. This transition region, sometimes called the post-merger phase, is particularly interesting because it bridges two different mathematical regimes. Understanding this transition requires matching numerical relativity simulations of the merger to perturbative calculations of the ring-down, a technical challenge that has only recently been overcome. The ring-down phase has also revealed surprises about black hole dynamics. For instance, the relative amplitudes of different quasi-normal modes don't always match simple theoretical expectations. Sometimes overtones are stronger than expected, or modes that should be suppressed by symmetry are nonetheless excited. These surprises don't contradict general relativity, but rather reveal the richness of black hole dynamics and the complexity of the merger process that excites the ring-down. The story of detecting gravitational waves from black hole mergers is one of the greatest scientific achievements of the 21st century, combining theoretical insights dating back to Einstein with cutting-edge technology that pushes the boundaries of what's measurable. The journey from theoretical prediction to experimental confirmation took exactly 100 years. From Einstein's publication of general relativity in 1915 to the first detection of gravitational waves in September 2015. This century-long quest involved thousands of scientists, billions of dollars in funding, and technological innovations that seemed impossible just decades ago. The idea of detecting gravitational waves experimentally began to take shape in the 1960s, when Joseph Weber at the University of Maryland built the first gravitational wave detectors. Weber's detectors were massive aluminum cylinders weighing several tons, instrumented with sensitive strain gauges that could detect tiny deformations. The idea was that a passing gravitational wave would cause the cylinder to ring like a bell, and this ringing could be detected. Weber claimed to have detected gravitational waves in 1969, but his results could never be independently confirmed, and it became clear that his detectors were not nearly sensitive enough to detect the weak signals from astrophysical sources. Despite the failure of Weber's bars to detect real gravitational waves, they inspired a generation of physicists to think seriously about gravitational wave detection. It became clear that detecting these incredibly weak signals would require a fundamentally different approach. The idea of using laser interferometry to detect gravitational waves was proposed independently by several scientists in the early 1970s, including Rainer Weiss at MIT, who laid out the basic design that would eventually become LIGO. The principle behind laser interferometry for gravitational wave detection is elegantly simple, though the implementation is extraordinarily challenging. A laser beam is split and sent down two perpendicular arms. The beams bounce off mirrors at the ends of the arms and recombine at the beam splitter. If the arms are exactly the same length, the recombined beams interfere constructively or destructively, depending on the exact setup. A passing gravitational wave changes the length of one arm relative to the other, altering the interference pattern in a measurable way. The challenge lies in the incredibly small size of the effect. Even the strongest gravitational waves from black hole mergers change the length of LIGO's 4-kilometre arms by less than 1/10,000th the width of a proton. Measuring such tiny changes requires isolating the mirrors from all sources of noise, seismic vibrations, thermal fluctuations, even the quantum fluctuations of the laser light itself. It's like trying to hear a whisper from across a football field during a rock concert. The development of LIGO was a decades-long endeavour that required solving countless technical challenges. The mirrors had to be suspended in sophisticated isolation systems that could filter out ground vibrations. The laser had to be stabilised to extraordinary precision. The entire 4-kilometre beam path had to be maintained in an ultra-high vacuum, better than interstellar space, to prevent air molecules from scattering the laser light. Each component had to be pushed to the limits of technological capability. Construction of LIGO began in the 1990s with 2 observatories built simultaneously, one in Hanford, Washington, and another in Livingston, Louisiana. Having 2 widely separated detectors is crucial for confirming that a signal is real and not just local noise, and for determining the direction to the source through triangulation. The initial LIGO operated from 2002 to 2010 without detecting any gravitational waves. Though this wasn't unexpected, the sensitivity required to detect the weak signals from cosmic sources was at the very edge of what was technologically possible. After the initial LIGO run, the detectors underwent a major upgrade to advanced LIGO, incorporating new technologies developed over the previous decade. The laser power was increased, the mirrors were made heavier and more reflective, the isolation systems were improved, and quantum squeezing techniques were implemented to reduce quantum noise. These improvements increased the sensitivity by a factor of 10, expanding the volume of universe LIGO could observe by a factor of 1,000. Advanced LIGO began its first observing run in September 2015, and within days it detected its first gravitational wave signal. On September 14th at 09:50:45 UTC, both LIGO detectors registered a signal lasting about 0.2 of a second, sweeping upward in frequency from 35 to 250 Hz. The signal was so strong and clear that it was initially suspected to be a test injection, a fake signal deliberately added to test the analysis pipelines. But it was real. Humanity had detected gravitational waves for the first time. The signal, designated GW1F0914, came from the merger of 2 black holes, about 36 and 29 solar masses, located about 1.3 billion light-years away. The match between the observed signal and theoretical predictions was remarkable, confirming not just the existence of gravitational waves, but also the reality of black holes and the validity of general relativity in the strong field regime. The detection was announced on February 11th, 2016, creating a sensation in the scientific community and beyond. Since that first detection, LIGO has been joined by other gravitational wave observatories. The Virgo detector in Italy came online in 2017, providing a third detector that greatly improves sky localization and parameter estimation. The Kagra detector in Japan, built underground in a mine to reduce seismic noise, began operations in 2020. Plans are underway for a LIGO India detector that will further expand the global network. Each new detection has revealed something surprising about black holes and their mergers. GW1F0914 showed that black holes of 30 solar masses exist and can merge within the age of the universe. GW17087 detected in August 2017, came from the merger of two neutron stars and was accompanied by electromagnetic signals across the spectrum, opening the era of multi-messenger astronomy. GW190521, detected in May 2019, involved black holes in the so-called mass gap, where stellar evolution theory suggested black holes shouldn't exist. The detection process itself is a marvel of data analysis. The raw data from the detectors is dominated by noise, seismic vibrations, thermal fluctuations, laser frequency noise, and countless other sources. The gravitational wave signals are buried deep in this noise, often barely visible even in optimal conditions. Extracting these signals requires sophisticated techniques, including matched filtering, where the data is compared to theoretical templates of what gravitational wave signals should look like. The matched filtering process involves comparing the detector data to hundreds of thousands of theoretical waveform templates, each corresponding to different combinations of black hole masses and spins. When the data matches a template above a certain statistical threshold, it triggers a detection candidate. These candidates are then subjected to rigorous statistical tests to determine whether they're real signals or just noise fluctuations that happen to look like signals. The collaboration between LIGO and Virgo involves over 1,000 scientists from around the world, working together to operate the detectors, analyze the data, and interpret the results. When a potential signal is detected, teams spring into action to verify its authenticity, determine its parameters, and alert the astronomical community for follow-up observations. This process, which once took months, now happens in near real time, with alerts sent out within minutes of detection. The technological innovations developed for LIGO have applications beyond gravitational wave detection. The isolation systems developed to protect the mirrors from vibrations are being adapted for other precision experiments. The ultra-stable lasers have applications in atomic clocks and quantum computing. The data analysis techniques developed to extract signals from noise are being applied to other fields, from medical imaging to financial analysis. Looking to the future, the field of gravitational wave astronomy is poised for explosive growth. Current detectors are being continuously upgraded, with plans to reach sensitivities that will allow them to detect black hole mergers throughout the observable universe. Next-generation ground-based detectors, like Cosmic Explorer and Einstein Telescope, will be 10 times more sensitive than current detectors, able to observe black hole mergers from the early universe when the first stars were forming. Space-based detectors, like LISA, planned for launch in the 2030s, will detect lower frequency gravitational waves from supermassive black hole mergers and from stellar mass black holes years before they merge. Pulsar timing arrays, which use millisecond pulsars as cosmic clocks, are searching for even lower frequency waves from the cosmic population of supermassive black hole binaries. Together, these different observatories will cover the entire gravitational wave spectrum, revealing the universe through gravitational eyes. The impact of gravitational wave astronomy extends far beyond the detection of black hole mergers. These observations are providing new tests of general relativity, new measurements of cosmic distances and the expansion rate of the universe, and new insights into the formation and evolution of black holes. They're revealing a population of black holes we didn't know existed, in mass ranges we thought were forbidden, with spins and orbits that challenge our understanding of stellar evolution. While the stellar mass black hole mergers detected by LIGO and Virgo are spectacular events, they pale in comparison to the mergers of supermassive black holes, behemoths millions or billions of times the mass of our Sun that lurk at the centres of galaxies. These cosmic giants merge as a consequence of galactic collisions, events that reshape entire galaxies and can influence the evolution of the universe itself. The merger of supermassive black holes represents gravitational physics at its most extreme scale, producing gravitational waves so powerful they can be detected across the observable universe, yet at frequencies so low that entirely different detection methods are required. Nearly every large galaxy harbours a supermassive black hole at its centre, a discovery that has revolutionised our understanding of galactic evolution. Our own Milky Way hosts Sagittarius A star, a black hole of about 4 million solar masses. The nearby Andromeda galaxy contains a black hole of 100 million solar masses. Some galaxies host even more massive monsters. The galaxy M87, famous for the first image of a black hole's event horizon, contains a black hole of 6.5 billion solar masses. The origin of these supermassive black holes remains one of the great mysteries in astrophysics. They appear to have formed very early in the universe's history. We observe quasars powered by billion solar mass black holes when the universe was less than 1 billion years old. Growing a black hole to such enormous size in such a short time challenges our understanding of black hole growth and suggests that the seeds of supermassive black holes formed through exotic mechanisms in the early universe. When galaxies collide, a process that takes hundreds of millions of years, their central black holes are eventually brought together by the complex dynamics of the merger. This process is far more complicated than the merger of stellar mass black holes, involving not just the black holes themselves, but the entire galactic environment. Billions of stars, vast clouds of gas and dust, and the dark matter halos that surround galaxies. The journey of two supermassive black holes toward merger begins when their host galaxies first interact. Galaxies are not solid objects, but collections of stars, gas, and dark matter held together by gravity. When two galaxies approach each other, their gravitational fields begin to distort each other's structure, creating tidal tails and bridges of stars stretching between them. These early interactions can trigger bursts of star formation as gas clouds collide and compress, lighting up the merging galaxies with new, hot stars. As the galaxies continue to merge, their central black holes, each sitting at the bottom of its galaxy's gravitational potential well, begin to sink toward the centre of the merged system. This process, called dynamical friction, occurs as the black holes gravitationally interact with the surrounding stars and dark matter. The black holes create wakes of slightly increased density behind them as they move, and these wakes pull back on the black holes, causing them to lose energy and spiral toward the centre. The two supermassive black holes eventually form a binary system, orbiting their common centre of mass. Initially, this binary is very wide, with the black holes separated by thousands of light years. At these separations, the orbital period is millions of years, and the gravitational waves produced are far too weak and low frequency to contribute significantly to orbital decay. The binary must lose energy through other mechanisms to bring the black holes closer together. This is where the process encounters what's known as the final parsec problem. As the binary black holes orbit, they gravitationally slingshot nearby stars, ejecting them from the central region. This process efficiently removes energy from the binary, causing the orbit to shrink. However, once the black holes have cleared out all the stars from their orbital region, this mechanism stops working. The black holes are left orbiting at a separation of about a parsec, 3 light years, with no obvious way to get closer. Several solutions to the final parsec problem have been proposed. If the galaxy merger funnels gas into the central region, this gas can form a circumbinary disk around the black hole binary. Gravitational torques from this disk can extract angular momentum from the binary, driving the black holes closer together. Alternatively, if the galactic center has a sufficiently high density of stars on eccentric orbits, these stars can continue to interact with the binary even after the circular orbits have been cleared. The environment around a supermassive black hole binary is unlike anything else in the universe. The black holes are orbiting through a dense stellar cluster, possibly surrounded by a disk of gas heated to millions of degrees. This gas glows brightly in X-rays, potentially making the binary visible to telescopes long before the merger. Some models predict that the gas forms mini-disks around each black hole, connected by streams of material flowing between them. These configurations could produce periodic variations in brightness as the black holes orbit, providing an electromagnetic signature of the impending merger. When supermassive black holes finally get close enough for gravitational wave emission to dominate their evolution, they produce waves at much lower frequencies than stellar mass black hole mergers. 2 billion solar mass black holes orbiting at a separation of a few hundred Schwarzschild radii would produce gravitational waves with periods of hours to days, far below the frequency range of ground-based detectors like LIGO. Detecting these waves requires entirely different techniques. The Laser Interferometer Space Antenna, or LISA, is a planned space-based gravitational wave observatory designed specifically to detect low-frequency gravitational waves from supermassive black hole mergers. LISA will consist of 3 spacecraft arranged in an equilateral triangle with sides 2.5 million kilometers long, orbiting the Sun in Earth's orbital path. Laser beams between the spacecraft will measure tiny changes in their separation caused by passing gravitational waves. LISA will be able to detect supermassive black hole mergers throughout the observable universe. A merger of 2 billion solar mass black holes would be visible to LISA even if it occurred when the universe was only a fraction of its current age. These observations will provide unprecedented insights into how supermassive black holes grow and evolve, how they influence galaxy formation, and how common such mergers are throughout cosmic history. Even lower frequency gravitational waves from supermassive black hole binaries that are still widely separated can be detected using pulsar timing arrays. Millisecond pulsars are incredibly stable cosmic clocks, rotating hundreds of times per second, with timing precision rivaling atomic clocks. A gravitational wave passing between Earth and a pulsar causes tiny variations in the arrival times of the pulsar's radio pulses. By monitoring many pulsars across the sky for years or decades, astronomers can search for the correlated timing variations that would indicate gravitational waves. Recent results from pulsar timing arrays have found evidence for a gravitational wave background at nanohertz frequencies, likely produced by the cosmic population of orbiting supermassive black hole binaries throughout the universe. This background is like a cosmic hum, the combined signal from thousands of supermassive black hole binaries, too faint to detect individually. Studying this background will reveal the merger rate of supermassive black holes across cosmic time and provide insights into galaxy evolution on the largest scales. The merger of supermassive black holes has profound effects on their host galaxies. The gravitational waves carry away not just energy, but also linear momentum, potentially giving the merged black hole a kick velocity of thousands of kilometers per second. Such a kick could eject the black hole from the galaxy entirely, leaving a galaxy without a central black hole. Alternatively, if the kick is smaller, the black hole might oscillate through the galaxy, disrupting stellar orbits and potentially triggering new rounds of star formation. The energy released in a supermassive black hole merger is almost incomprehensible. 2 billion solar mass black holes merging would convert about 100 million solar masses into gravitational wave energy, more than the total mass of all the stars in a dwarf galaxy. This energy is released over a period of hours to days, making the merger briefly the most powerful gravitational wave source in the universe. Yet because this energy is in gravitational waves rather than light, the merger might be invisible to traditional telescopes unless there's surrounding gas that's heated by the process. Supermassive black hole mergers also offer unique tests of general relativity. The enormous masses involved mean that the black holes move relatively slowly, even in the final stages of merger, allowing for precise tracking of the orbital evolution. Any deviation from general relativity's predictions would accumulate over many orbits, making these systems sensitive probes of gravitational physics. The merger and ring-down phases probe the nature of black hole event horizons on scales millions of times larger than stellar mass mergers. The cosmological implications of supermassive black hole mergers extend beyond the events themselves. These mergers are standard sirens that can be used to measure cosmic distances independently of other methods. If a merger has an electromagnetic counterpart that allows identification of the host galaxy, the gravitational wave signal provides a direct distance measurement that can be used to study the expansion history of the universe and the nature of dark energy. Looking ahead, the detection of supermassive black hole mergers will open an entirely new window on the universe. We'll be able to trace the growth of supermassive black holes from the early universe to the present day, understand how they co-evolve with their host galaxies, and witness some of the most energetic events in the cosmos. These observations will likely reveal surprises, just as LIGO's detections have revealed unexpected populations of stellar mass black holes. As we stand at the dawn of gravitational wave astronomy, having detected barely 100 black hole mergers in less than a decade of observations, the future promises revelations that will fundamentally reshape our understanding of the universe. The trajectory of discovery ahead of us spans from technological marvels that will increase our sensitivity 1,000-fold to theoretical breakthroughs that may finally reconcile general relativity with quantum mechanics, to observations that could reveal the nature of dark matter and dark energy. The story of black hole mergers, which began as mathematical curiosities in Einstein's equations, is evolving into one of the most powerful tools for probing the cosmos. The immediate future of black hole astronomy lies in the continuous improvement of existing detectors. LIGO and Virgo are not static instruments, but are constantly being upgraded with new technologies. The implementation of quantum squeezing, where the quantum noise in the laser light is redistributed to improve sensitivity at specific frequencies, has already improved detection rates significantly. Future upgrades will include larger mirrors with better coatings, more powerful lasers, and improved isolation systems. These incremental improvements will gradually expand the volume of universe we can observe, revealing ever more distant and exotic black hole mergers. The next major leap will come with the construction of third-generation ground-based detectors. The Einstein telescope, planned for construction in Europe, will be built underground to reduce seismic noise and will feature arms 10 kilometers long, more than twice the length of LIGO's arms. Its triangular configuration with 6 interferometers will provide redundancy and improved sky coverage. Cosmic Explorer, proposed for construction in the United States, will have arms 40 kilometers long, 10 times longer than LIGO. These massive instruments will be sensitive enough to detect every stellar mass black hole merger in the observable universe. With third-generation detectors, we'll be able to observe black hole mergers from the epoch of first star formation, when the universe was only a few 100 million years old. These primordial mergers will tell us about the properties of the first generation of stars, which formed from pristine hydrogen and helium without the heavy elements that influence star formation today. We'll learn whether these first stars were truly as massive as theories predict, potentially hundreds of times the mass of our Sun, and whether they produced a population of intermediate mass black holes that could be the seeds of today's supermassive black holes. The improved sensitivity will also allow us to extract far more information from each merger. Instead of just measuring masses and spins, we'll be able to detect subtle effects, like orbital eccentricity, which carries information about how the binary formed. We'll measure multiple ring-down modes with high precision, allowing stringent tests of the no-hair theorem. We might even detect the gravitational memory effect, a permanent distortion of spacetime that persists after the gravitational waves have passed, like a cosmic scar left by the merger. Space-based detection with LISA will revolutionize our understanding of supermassive black holes. LISA will observe these behemoths as they spiral together over months or years, tracking thousands or millions of orbits with exquisite precision. This will allow unprecedented tests of general relativity in the strong field regime, potentially revealing deviations that could point toward quantum gravity. LISA will also detect extreme mass ratio in spirals, stellar mass black holes spiraling into supermassive black holes, which probe the space-time geometry around the larger black hole with extraordinary precision. The multi-band astronomy enabled by having both ground-based and space-based detectors will be particularly powerful. Some stellar mass black hole binaries will be visible to LISA years before they merge, allowing us to predict when and where they'll appear in LIGO's frequency band. This will enable targeted electromagnetic observations of the merger, searching for any light produced by surrounding gas or other exotic phenomena. For supermassive black hole mergers, we might observe the early in spiral with pulsar timing arrays, the late in spiral and merger with LISA, and potentially electromagnetic counterparts with traditional telescopes. Pulsar timing arrays are on the verge of detecting individual supermassive black hole binaries, not just the background hum from the cosmic population. As timing precision improves and more pulsars are monitored for longer periods, we'll be able to map the gravitational wave sky at nanohertz frequencies, identifying specific galaxies hosting binary supermassive black holes millions of years before they merge. This will provide a complete census of supermassive black hole binaries in the nearby universe and reveal how common galaxy mergers truly are. The theoretical understanding of black hole mergers continues to advance alongside observational capabilities. Numerical relativity simulations are becoming ever more sophisticated, incorporating effects like orbital eccentricity, precession, and even the influence of surrounding matter. Machine learning techniques are being applied to speed up waveform generation, allowing us to explore vast parameter spaces that would be computationally prohibitive with traditional methods. These advances will be crucial for extracting maximum information from the flood of data that next-generation detectors will provide. One of the most exciting possibilities for the future is the detection of exotic compact objects that might masquerade as black holes. Some theories predict the existence of boson stars, self-gravitating configurations of scalar fields that could be dark matter candidates. Others suggest gravastars, objects with a de Sitter space interior surrounded by a thin shell of matter. These exotic objects would merge differently than black holes, producing distinctive gravitational wave signatures. Even a single confirmed detection of such an object would revolutionize physics. The connection between black hole mergers and cosmology will become increasingly important. As we detect mergers at greater distances, we'll be able to trace the evolution of the black hole population across cosmic time. This will reveal how the merger rate depends on cosmic epoch, what role mergers play in black hole growth, and how black holes influence galaxy evolution. Gravitational wave observations might even constrain the nature of dark energy by providing independent distance measurements to high redshift. Multi-messenger astronomy, combining gravitational wave observations with electromagnetic and neutrino observations, will mature into a powerful tool for understanding the universe. While black hole mergers are generally not expected to produce electromagnetic signals unless they occur in gas-rich environments, the ability to quickly localize mergers and trigger follow-up observations will occasionally reveal surprises. We might discover that some black hole mergers do produce light through exotic mechanisms, or that they trigger observable effects in their surrounding environment. The role of black hole mergers in addressing fundamental questions in physics will expand. These events probe gravity in its most extreme regime, where the field is strong, dynamical, and highly nonlinear. Any theory of quantum gravity must reproduce general relativity's predictions for black hole mergers, while potentially predicting small deviations that could be detected with sufficient sensitivity. Black hole mergers might reveal whether spacetime is fundamentally continuous or discrete at the smallest scales, whether information can truly be destroyed in black holes, and whether our universe has extra dimensions beyond the familiar three of space and one of time. Artificial intelligence and machine learning will play an increasingly important role in black hole astronomy. These techniques are already being used to identify signals in noisy data, classify events, and estimate parameters. As the volume of data grows exponentially with improved detectors, AI will become essential for real-time analysis, identifying interesting events for detailed study, and discovering unexpected patterns in the data. Machine learning might reveal new types of sources or phenomena that we haven't even imagined. The cultural and philosophical impact of black hole astronomy will continue to grow. Each detection is a reminder of the universe's vastness and violence, of phenomena so extreme they challenge our everyday understanding of reality. The ability to observe events that occurred billions of years ago, to witness the collision of objects where space and time lose their ordinary meaning, connects us to the cosmos in a profound way. Black hole mergers have already captured the public imagination, and future discoveries will undoubtedly inspire new generations of scientists and thinkers. Educational opportunities arising from black hole astronomy are expanding rapidly. The data from gravitational wave detectors is publicly available, allowing students and citizen scientists to participate in the analysis. Simplified versions of the detection algorithms can run on personal computers, letting anyone search for black hole mergers in real data. This democratization of astronomy will broaden participation in science and potentially lead to unexpected discoveries by non-professionals who bring fresh perspectives to the data. International collaboration in black hole astronomy serves as a model for how humanity can work together on grand challenges. The detection of gravitational waves requires a global network of detectors, with data shared freely among thousands of scientists from dozens of countries. This collaboration transcends political boundaries and demonstrates that our greatest achievements come when we pool our resources and expertise toward common goals. Future projects like the Einstein Telescope and Cosmic Explorer will require even greater international cooperation. The technological spin-offs from black hole astronomy will benefit society in unexpected ways. The extreme sensitivity required to detect gravitational waves has driven innovations in laser stabilization, vibration isolation, vacuum technology, and quantum optics. These technologies have applications in fields ranging from quantum computing to precision manufacturing. The data analysis techniques developed for finding signals in noise are being applied to medical imaging, financial modeling, and climate science. Looking further into the future, we can imagine even more ambitious projects. Space-based detectors larger than LISA could observe gravitational waves from the early universe, potentially detecting signals from cosmic inflation or phase transitions in the primordial plasma. Networks of detectors on the Moon, free from seismic noise, could achieve sensitivities impossible on Earth. Gravitational wave telescopes might eventually become as common as optical telescopes, with specialized instruments for different frequency ranges and source types. The philosophical implications of black hole astronomy extend to questions about the nature of knowledge itself. We're observing events that occurred billions of years ago in regions of space we can never visit, under conditions we can never recreate in laboratories. Yet through the combination of theoretical understanding and precise measurement, we can know intimate details about these events, the masses of the black holes, their spins, their distance from us. This demonstrates the power of the scientific method to extend human knowledge far beyond our direct experience. As we continue to observe black hole mergers, we're building a new kind of astronomy, one based not on light, but on the fabric of space-time itself. Each detection adds to our understanding, revealing patterns and raising new questions. We're learning that black holes are not rare, exotic objects, but common features of the universe, playing crucial roles in galaxy evolution and cosmic structure formation. The universe is far more dynamic and violent than we imagined, with black holes merging throughout cosmic history, each event reshaping space-time and sending ripples across the cosmos. As our journey through the remarkable phenomenon of black hole mergers draws to a close, we find ourselves at a unique moment in human history. For the first time, we can detect and study events of such extreme violence and beauty that they shake the very fabric of reality itself. The ripples in space-time from merging black holes have travelled billions of years to reach us, carrying messages from epochs when the universe was young, when the first galaxies were forming, when the cosmic story was still being written in its early chapters. What we've explored tonight represents one of humanity's greatest intellectual achievements: the prediction, detection, and understanding of gravitational waves from black hole mergers. From Einstein's equations scribbled on paper in 1915 to the chirp detected by LIGO exactly 1 century later, this story demonstrates the power of human curiosity and ingenuity. We've built instruments capable of measuring distances smaller than an atomic nucleus. We've developed mathematics to describe the indescribable, and we've confirmed predictions about nature's most extreme phenomena. The universe revealed by black hole mergers is one of constant change and spectacular violence, yet also one of profound order and mathematical beauty. Every merger follows the same fundamental laws, whether it involves black holes of 3 solar masses or 3 billion solar masses, whether it happened yesterday or 10 billion years ago. This universality, the fact that the same equations describe phenomena across such vast ranges of scale and time, suggests a deep unity underlying the apparent complexity of the cosmos. As you drift off to sleep tonight, perhaps you'll dream of these cosmic dances, of regions where time slows to a crawl and space bends back on itself, of ancient collisions whose echoes are only now reaching Earth. Remember that even as you rest, gravitational waves from countless mergers are passing through your body, stretching and compressing space by infinitesimal amounts, connecting you directly to the most violent events in the universe. You are, quite literally, in touch with the cosmos, the story of black hole mergers is far from complete. We've only just begun to explore this new spectrum of the universe, and already we've found surprises. Black holes more massive than theory predicted, mergers more common than we expected, spins and orbits that challenge our understanding of stellar evolution. As our detectors improve and new observatories come online, we'll undoubtedly discover phenomena we haven't even imagined. Perhaps we'll find evidence of new physics beyond general relativity, or discover that dark matter consists of primordial black holes, or observe the merger of exotic objects that shouldn't exist according to our current theories. The story of black hole mergers is far from complete. We've only just begun to explore this new spectrum of the universe, and already we've found surprises. Black holes more massive than theory predicted, mergers more common than we expected, spins and orbits that challenge our understanding of stellar evolution. As our detectors improve and new observatories come online, we'll undoubtedly discover phenomena we haven't even imagined. Perhaps we'll find evidence of new physics beyond general relativity, or discover that dark matter consists of primordial black holes, or observe the merger of exotic objects that shouldn't exist according to our current theories. This is where you come in. The future of black hole astronomy, and indeed all of science, depends not just on the scientists working today, but on the next generation of curious minds, who will ask new questions, develop new techniques, and make discoveries we can't yet imagine. Whether you're a student considering a career in science, an amateur astronomer fascinated by the cosmos, or simply someone who looks up at the night sky with wonder, you're part of this grand adventure of understanding our universe. The data from gravitational wave detectors is publicly available, waiting for fresh eyes and new perspectives. Students around the world are already making contributions to this field, developing new analysis techniques, searching for subtle signals that might have been missed, and asking questions that challenge established thinking. You don't need access to $1 billion detector to participate in this revolution, just curiosity, dedication, and perhaps a computer to analyze the freely available data. Consider the profound privilege we have to live in this moment. For all of human history until just a few years ago, black hole mergers were invisible to us, their gravitational waves passing through Earth undetected. Our ancestors could only wonder about the nature of gravity, about what happens when massive objects collide, about whether Einstein's wild predictions could possibly be true. Now we know. We've heard the universe sing in gravitational waves. We've witnessed the collision of objects so dense that a teaspoon of their material would weigh as much as a mountain, and we've confirmed that space-time itself can ripple and wave like the surface of a pond. The implications of these discoveries extend far beyond astronomy and physics. They remind us that the universe is far stranger and more wonderful than our everyday experience suggests. They show us that with sufficient ingenuity and determination, humans can understand phenomena that occur in realms completely beyond our direct experience. They demonstrate that international collaboration and the free exchange of ideas can achieve what no single nation or institution could accomplish alone. And they inspire us to keep pushing the boundaries of knowledge, to keep asking what if and why and how. As you've listened to this story of black hole mergers, perhaps you felt a sense of awe at the scale and violence of these events, or amazement at the precision with which we can now measure them. Perhaps you've been inspired by the century-long journey from theoretical prediction to experimental confirmation, or intrigued by the mysteries that remain unsolved. Whatever your reaction, remember that this is your universe too. These gravitational waves pass through you. These black holes are part of your cosmic heritage, and the questions they raise are yours to ponder. The universe revealed by gravitational wave astronomy is dynamic, violent, and beautiful in ways we're only beginning to appreciate. Every few days, somewhere in the observable universe, two black holes spiral together and merge, sending ripples through space-time that eventually wash over Earth. Each of these events is unique, encoding information about the black hole's masses, spins, and history. Yet each also follows the same fundamental laws, the same elegant mathematics that Einstein discovered over a century ago. This combination of diversity and unity, of chaos and order, of violence and beauty, is what makes the study of black hole mergers so captivating. Think about what we've learned just in the past few years. We've discovered that stellar mass black holes can be much more massive than traditional stellar evolution theory predicted, with some exceeding 50 or even 100 solar masses. We've observed black holes with extreme mass ratios merging, challenging our understanding of how such systems form. We've detected black holes spinning at nearly the maximum rate allowed by general relativity, their event horizons dragged around by the rotation of space-time itself. Each discovery raises new questions and opens new avenues for exploration. The rate at which we're detecting black hole mergers has exceeded even optimistic predictions. Scientists initially thought neutron star mergers would be more common than black hole mergers in our detectors, but the opposite has proven true. We're detecting roughly one black hole merger per week when our detectors are operating, building up a catalogue that's beginning to reveal patterns in the population of black holes throughout the universe. This abundance of detections is teaching us that black holes are not rare, exotic objects, but common features of the cosmic landscape, playing crucial roles in the evolution of galaxies and the universe itself. Looking ahead, the next few decades promise revolutionary discoveries. The detection of supermassive black hole mergers will reveal how these giants grow and influence galaxy evolution. We might observe black holes from the very first generation of stars, formed when the universe was only a few 100 million years old. We could discover entirely new types of compact objects, or find that black holes can form through mechanisms we haven't yet imagined. Each possibility is more exciting than the last, and all are within reach of planned observatories. The philosophical implications of studying black hole mergers are profound. These events probe the limits of physical law, regions where our familiar concepts of space and time break down. They force us to confront questions about the nature of information, causality, and reality itself. Some theories even suggest that each black hole could contain another universe, that our own universe might exist inside a black hole in a higher dimensional space. While these ideas remain highly speculative, the fact that we can even pose such questions scientifically shows how far our understanding has come. The technology developed for detecting gravitational waves is already finding applications in other fields. The exquisite isolation systems that protect LIGO's mirrors from vibration are being adapted for other precision experiments. The data analysis techniques developed to find faint signals in noise are being applied to medical imaging, helping doctors detect diseases earlier. The international collaboration model pioneered by gravitational wave astronomy is being adopted by other big science projects. In pushing the boundaries of what's measurable, we've developed tools and techniques that benefit society in unexpected ways. Education and public engagement around black hole mergers have brought the excitement of cutting-edge science to millions of people worldwide. The chirp of a black hole merger has become as iconic as the images of nebulae or galaxies that inspired previous generations. Students are using real gravitational wave data in classroom exercises, learning not just about black holes, but about how science actually works. The painstaking analysis, the careful verification, the gradual building of understanding from individual observations. This hands-on engagement with real scientific data is training the next generation of scientists and creating a more scientifically literate society. The cultural impact of discovering gravitational waves and black hole mergers extends beyond science. These discoveries have entered popular culture, inspiring art, music, and literature. They've become metaphors for transformation, for the power of patience and persistence, for the beauty that can emerge from violence. They remind us that we're part of something much larger than ourselves, that we're connected to cosmic processes of unimaginable scale and power. In an age often dominated by small concerns and immediate problems, black hole mergers lift our gaze to the infinite. As we conclude this journey through the phenomenon of black hole mergers, take a moment to appreciate the extraordinary time in which we live. We are the first generation in human history to hear the gravitational waves from colliding black holes, to measure the ripples in spacetime from events billions of light years away, to confirm Einstein's most extreme predictions. We've witnessed the birth of an entirely new form of astronomy, one that observes the universe not through light but through the fabric of spacetime itself. The story we've shared tonight, from the formation of black holes in the hearts of dying stars, through their long spiral toward each other, to the violent reorganization of spacetime as they merge, is both an ending and a beginning. It's the end of two black holes as separate entities, but the beginning of a new larger black hole. It's the end of a journey that might have lasted billions of years, but the beginning of gravitational waves that will travel for billions more. And for us, it's the end of one chapter in our understanding of the universe, but the beginning of a new era of discovery. So as you drift off to sleep, carried by thoughts of cosmic collisions and rippling spacetime, remember that you're part of this grand cosmic story. The atoms in your body were forged in the hearts of stars, possibly in the same stellar nurseries that produced black holes now merging in distant galaxies. The gravitational waves from those mergers pass through you, connecting you directly to events of unimaginable power and beauty. You are, in the most literal sense, a part of the universe becoming aware of itself, participating in the cosmic journey of discovery that began with the first humans who looked up at the night sky and wondered. If this journey through the world of black hole mergers has sparked your curiosity, if you found yourself amazed by the elegance of Einstein's equations or the ingenuity of gravitational wave detectors, if you want to learn more about these cosmic phenomena or share this wonder with others, then please like this video, subscribe to the channel, and join our community of cosmic explorers. Together, we'll continue to explore the mysteries of the universe, one gentle, thoughtful conversation at a time. Share this video with someone who might enjoy pondering the vastness of space as they drift off to sleep, someone who finds comfort in knowing that even in the apparent chaos of cosmic collisions, there is order, beauty, and profound meaning.